So just very quick introduction. This is our final keynote for the conference. I'm delighted to welcome a friend, a colleague, and a while ago a PhD supervisor, Karen Anderson, and her current PhD student, Brianna Pickstone, who's worked with me previously, and it's wonderful to see the ideas. Now, you were promised a little bit of controversy. That's been trundling on in conversations in the margins of the conference, but I think it should be really refreshing to hear what we've got coming up. Take photos of the QR codes so that you can join in.
Yeah, so just before we start, there are a few bits throughout the presentation I'm going to ask to engage us in a Mentimeter. So if you could just sign up into the codes there, and then it won't be for a little while, but just so that you're all prepared when it does come up.
Yeah. Okay. Right, so great to see everyone here this morning. Thanks for joining. This is a sort of interesting intervention, this talk, into what has been quite a technical conference, and we're going to kind of come at you this morning with a bit of philosophy. I'm joining here really as a sort of physical remote sensor. My background is in sort of spectral signatures and fine-grained data, and Bri is here in the context of her work as a sort of machine learning expert. And so we came up with this title together, partly because, from my perspective at least, I've seen over the past few years an increasing kind of melding between Earth observation and machine learning, such that, you know, often those two things always come hand in hand. And I think we need to sometimes go back to the physical basis of remote sensing and think about that as a context for the work that we're doing and the applied uses of machine learning. So today we're going to present this talk more as a conversation between me as a physical remote sensor and Bri as the machine learning expert, because both of us are interested in how to sort of optimally leverage information out of data, but also we're conscious of the need to kind of be transparent and physically meaningful in that process. And Bri has the really difficult task of sort of walking a line between those two fields in exploring the uses of machine learning and remote sensing in a sort of biodiversity net gain context. So most of what we're going to present today relates to machine learning applied to Earth observation data to retrieve land cover variables, but the concepts in this talk are kind of broadly applicable to all different kinds of Earth observation. And I guess the other thing to say, the kind of health warning, is that we don't have all the answers, but we do have a lot of questions, and I guess the goal is to sort of fertilise a bit of debate in the room. So let's start with something that brought us to where we are now. Al Gore, maybe you know this, maybe not, but he's probably one of the key people who brought us to this point where during his 1998 speech when he was Vice President of the US, he proposed the idea of a digital Earth, a comprehensive and objective replica of the planet that could be used for education and research. And he envisioned this system where anybody could interact with a 3D globe and access vast amounts of information about the Earth and its systems. And that's basically what we're all here for, right? Is we're using now these huge archives of data and we're processing those data through computers and machines, sometimes, and in fact often, increasingly often on the cloud. So the development of things like Google Earth and things like queryable or codable virtual globes can be seen as a realization of his digital Earth vision, allowing us to explore all kinds of dynamic systems. But I wonder if his statement here remains still true to this day, because since 1998, although we've seen a huge surge in digital data, and alongside this growth in machine learning and deep learning, that actually might mean that the images, even if they're being analysed, may not be being seen by a human brain. And that's an interesting sort of philosophical point to begin with. So we're now amidst a situation where there are more Earth observation satellites in orbit than ever before, and some industry forecasts project a tripling of Earth observation infrastructure in orbit within the next decade. And the challenge is that as more and more and more Earth observation data are being assimilated into the ecosystem, and particularly as the resolution of those data become finer and finer in time, space, spectral domains, then there becomes a sort of growing promise that machine learning and deep learning will increasingly make sense of those data for us.
And that's where you've probably seen a graph like this before, where over the past few decades we increasingly see the uptake of machine learning and deep learning, especially when applied to Earth observation data. And what kind of started off as this niche area of research has now skyrocketed into a rapidly evolving field. And together they've been recognized as key tools to unlocking new insights into the Earth, which is essentially what we've seen over the past few days. And what started with statistical models has now progressed into support vector machines and now into the deep learning models like convolutional neural networks. And this rapid growth has been made possible through advances such as data availability, powerful computing, and of course the democracy of the cloud, and this rise of open access satellite imagery. But on the other hand, the other reason why we see this is because we want to make, I'm sure you're here today, because you want to make some form of environmental good for the world. And we want it to change it for the better using this geospatial information. But what if we instead, what we might see as a controversial provocation, is that the proliferation of Earth observation machine learning actually generates harm. So that can include environmental harm and what you consider like things like putting the rockets out and launching those rockets into the space junk that we see through dying satellites, or the huge consumption of things like the carbon and water to fuel those data centers. But it might also be things like social harm. So for example, there's a place called Ashburn in the USA, which has seen that there's currently uprising against the huge rise that they're seeing of data centers in their town. And there are also ethical considerations, like feeding the machines uncritically and what might transpire from that. So this is the dualism of our discipline. So how do we leverage something that we know and now know is potentially has a dark side to deliver good outcomes? It's like this tightrope walk, and as something working in this field, and someone who's earlier in their career research, it's something that I feel at a personal level and also consider nearly every day when I'm conducting these machine learning and Earth observation workflows.
Okay, so at this point we're going to take you on a slightly deep dive into some philosophy, because sometimes philosophy can provide us some answers, or at least some points to think around and talk around. And for me, the work of the philosopher Donna Haraway here is quite relevant. Now, she is a very famous philosopher, but she's better known within the artistic and the creative community. So actually, before we kind of start telling you about her work, it would be useful if you could log on to Menti and just tell us how many of you have come across Donna Haraway, how many of you know her work, because it would be really interesting to see in this room of technologists and technology-enabled people how many people have actually come across her. So let's go to Menti. Where's Menti? Is it? Here we go. Okay. So there we go. The results are in. How many people have heard of Donna Haraway? 1. Maybe that equals 3, because, oh no, 2. But you see the kind of imbalance, and I guess what we want to do today is to perhaps try to bring some of that dualism to life by sort of engaging a little bit with Haraway, and this will be relatively superficial because her work is quite deep, and we've only got a few minutes to kind of explain to you why she might help us to think about this challenge. So it's kind of weird that scientists don't know her, because her focus is very much on science and technology studies, and she's best known for her influential concept of the cyborg, which she defines as a hybrid of human and machine. I'll come back to that in a moment. And I think her work provides a really interesting lens through which we can think critically about this recent emergence of big machines in an era of big Earth data. So in her 1985 Cyborg Manifesto, bearing in mind this is really old work, right, 1985, she says, late 20th century machines have made thoroughly ambiguous the difference between natural and artificial, mind and body, self-developing and externally designed, and many other distinctions that used to apply to organisms and machines. And I think this is a very relevant statement in the context of the work that we kind of have seen over the last couple of days. In remote sensing, algorithms like CNNs, for example, might forge interpretations of spatial data, mapping things like forest health or land cover change. And these are models which blur the line between nature and technology. Machine learning systems are designed by humans, yet they can evolve or self-develop by adapting to data, so we allow the machine mind to apply itself to the Earth's body here. And by frighteningly inert humans, I think she means that as humans it's easy to become passive consumers of the outcomes of these machines, and this is something that she very much warns against. Now, I want to take you into a very deep and dark dive into the mind of Donna Haraway. You can do that yourself after this if you feel so inclined to read her work. But I think it's also useful to kind of briefly pause here on a paper that she wrote slightly later. This was in 2013, a paper on situated knowledges. Here she returns to the point of the image, which is very specifically related to what we're talking about today. And here she considers the view from above that satellites deliver. She says, for example, that the eye of an ordinary primate like us can be endlessly enhanced by these satellite surveillance systems. And what she means by that is that in this seemingly miraculous expansion of human sight, we encounter something quite seductive, and there are so many different possibilities for using that view from above to do good or otherwise. You know, we see the sort of whole spectrum of remote sensing, from militaristic applications through to humanitarian ones. So she might call that a sort of monstrous capability of the technology, and that's because she defines this view of Earth from space as something that's superhuman and something that she calls the God trick. This image that you see here is a nice sort of rendering of that God trick. It's an image of Europe from the Copernicus satellite. It was generated between October 2022 and 2023, and it's the kind of product we all maybe blindly consume as remote sensing scientists, but it's not real, okay? It's a perfect example of Haraway's God trick, because it's a view of something from nowhere. It's a mosaic of images, all captured from different viewpoints, all captured at different points in time, and sort of cleaned up and stuck together to produce this smoothed mosaic. So, as consumers of such data, we view the Earth in these pixels and data streams, and sometimes our only encounter with the data is through code that's typed into a browser window or something like that, talking to a computer somewhere. So coming back to Bree's point about these data centres, we often don't even know where those are. So there's these sort of unsituated transactions on the cloud computing infrastructure, where we're rendering the world as image, but we can easily forget who is watching, from where, how and why. So these are all kind of really important, critical geographic concerns. So just to kind of finally finish up, one of the things that Haraway says, and she doesn't have a lot of good things to say about this, you might have got the sense of that by now, but she basically says that this can produce something called techno-monsters. Techno-monsters are these hybrid beings made of flesh, code, optics and ideologies. And so when we talk about Earth observation and machine learning amidst this age of rapid growth, I think we have to stop and think about what she has to say and ask quite urgently, what kind of vision are we practicing, and what kind of truth does it claim to offer, and more importantly maybe at what environmental, social, ethical kind of costs. So I'm coming at this from a person who did her PhD at the time when if you wanted an image from NASA you had to write a letter and put it in the post, and about 2 to 3 months later they would send you a DVD. And that DVD might contain one Landsat scene or one scene from MODIS or something like that. And to extract the information from that image required me going to a different building on campus, logging into a Unix workstation and building up the code very slowly. And the generation before me were doing this with piles of punch cards. So this data and computational poverty at that time led to a sort of period of philosophical innovation within physical geography, within remote sensing, where people were asking these fundamental questions about what is in an image. Like, what are we looking at? What does this data represent? And from that early work, particularly early work around the 1980s and 90s by American geographers like Woodcock and Strahler, sort of emerged a series of answers to fundamental questions like, what happens if you make the spatial resolution finer in an image? How does the information change? And I really like these two examples that you can see on here. You can have a read of those papers in your own time, but they're not isolated examples. There's many of these if you go back into remote sensing of environment in the 1980s. They answer some really fundamental questions that I think we've lost sight of in the current boom of particularly fine spatial resolution data and big machine learning. But the problem with these hyper-focused studies in the era of data poverty was that they didn't deliver on the big mission goal of remote sensing, right? They didn't, as was shown in that last presentation, save the world, right? They were very sort of inward-looking, and they didn't bring about positive change by enhancing sort of environmental understanding. Actually, yeah, that's a key point. What they did show was that finer resolution data does not always equal better quality information. So that's a key point to remember. And of course, what's different now is that we're sort of amidst a series of global crises. The climate change and biodiversity crisis are just a couple of examples. The doomsday clock is ticking closer to midnight, and we need to urgently find ways to capitalise on this huge data bank that we're building up in Earth observation to solve the crises. And so a lot of the work that we've seen over the last few days is sort of trying to do that. But coming back to the point that Earth observation and machine learning does environmental harm that Bree showed earlier, the goal of all of us should, I guess, try to be maybe to do no net harm, or ideally to do net good for the environment and society through the things that we're using these data for. So what we want to try to do in the rest of this talk is to sort of look at some of these older concepts and use those to shine a lens on the biodiversity crisis in particular, because that's what Bree's PhD is about, but to think critically about some of that older work which situates remote sensing in that critical framework of what's in an image, what are data made up of, and to think about how we sort of best and most responsibly use remote sensing and machine learning to answer that question.
So as Karen mentioned, my PhD is specifically focusing on the biodiversity crises, specifically here in the UK. And some of you will probably know that it's the most depleted, one of the most depleted countries in the world. And the State of Nature report has shown a 19% decline in biodiversity since the 1970s, with now 1 in 6 species threatened with extinction. However, at the same time, we have this global commitment under the Sustainable Development Goals to push for advances in infrastructure development, and on the same hand, trying to end biodiversity loss through SDG 14 and 15. So because of this global commitment, there's been a huge outsurge of different biodiversity offsetting strategies that have happened around the globe. And I'm particularly focusing on biodiversity net gain here in the UK, which became mandatory in February 2024. And along with that, we have seen a more sustainability-focused development, and this also means that each habitat needs to show, or each development project needs to show a 10% in biodiversity. But when I've been looking at this and trying to figure out exactly how machine learning and Earth observation could fit in trying to solve, or maybe not solve, but help assist with some of the biodiversity net gain problems, I've been reading lots of literature, looking at Earth observation data, and when you first look at what's happening in academia, you get this, or this is an example of what you get. So here is an image which shows what's happening within academia of how machine learning has been applied specifically to Earth ecosystem services. And you can see here that over 308 publications with ecosystem services, you end up with many different studies lacking rigor of how they're reporting machine learning. And in fact, here's just 2 that I've pointed out at this, here, which is 59% do not report testing the generalizability of the model, and 43% even failed to report any model settings. So perhaps this is a manifestation of Donald Haraway, which called the techno monster, this blind, hungry feeding of algorithms with huge data, often without clear justification and without delivering ecological insight. So what does all this computational effort end up actually producing? At worst, as a result of this gluttony, we could argue that alongside biodiversity loss, we're also producing algorithmic waste. and very little actual progress in ecological understanding. So in this rush that we see of technological solutions, we risk solving for the wrong thing or solving nothing at all. So there's no real gain in understanding and certainly no real gain for biodiversity. So then what if I consider what's happening outside of academia and what's happening in industry? And since February 2024 of the release of Biodiversity Net Gain, there has been a range of different products that have come about of using AI technology and Earth observation to help with biodiversity net gain. And there's been about 13 companies that I've found so far that use this and that are implementing to try and say that they trying to help with biodiversity net gain. But when we look at what they're doing, there's very little transparency of what's happening. So some are just saying our scientific programs makes it much, much more accurate, or just reporting that what the deep learning or AI, deep learning or machine learning models they use, just simply writing AI technology. And so without that transparency, it's very difficult for researchers like myself, regulators or land managers to evaluate the credibility or robustness of what's being sold. So it risks turning B&G into a tick box exercise driven by opaque algorithms rather than ecological understanding. So a goal in my PhD, which I'm doing in partnership with an ecological consultancy company, is to try and make these methods more interpretable and a little bit more transparent. And this kind of more openness approach is important so that solutions can be applied at scale and also are generalizable.
Okay, so we're going to delve into some more detailed aspects in a moment, but just before we do that, we're going to close the introduction of this talk by sort of proposing to you all that we are Haraway's cyborgs already. Okay, as I said, she defined this as being something that transgressed boundaries, so a biological organism using a machine to enhance its understanding of the natural world, which sounds like a pretty reasonable description of all of us. And so, yeah, I guess, maybe we can even ask people, how many of you use AI tools, ChatGPT or whatever, to clean up your code or something like that? I'm sure if we asked that question, there would be lots of people doing that kind of thing. So, given that we can probably accept that we're cyborgs, perhaps it's time to think about how we might become better ones. And sorry to use such a kind of crude analogy, but what we want to avoid is the sausage factory that leads to uncritical and unregulated data or machine learning gluttony, as Bree's last slide shows. So that's where we feed the machine with data, but we don't do that carefully. And what the machine spits out is a sausage of unknown origin, which nobody wants to eat. So we need to move forward towards this sort of more efficient and critically meaningful engagement with the machine, and limiting that engagement with the machine to only the most useful elements because we recognise the risks and the environmental implications. So what we're going to do from here on is sort of explore a bit more deeply and technically what Haraway means by the God trick, and identifying various tricks of Earth observation data and discussing how some of those concepts might relate to the machine learning task. So I'm going to start with the sort of very obvious one, which is the trick of the pixel. And one of the big philosophical and technical challenges posed by Earth observation data is that of the pixel. Most of you will know Minecraft or something similar to that, where the world is rendered as a series of blocks, and the world doesn't look like that really, but in fact that's what we are sort of presented with when we look at grids of pixels from Earth observation data. In fact, Earth observation data are mostly worse models of the world than Minecraft because there's no volume to the pixel world, generally speaking, and we're compressing the Earth to a two-dimensional grid. And back in the 1990s, a critical geographer called Peter Fisher, a GIS professor at Leicester University, wrote some really good stuff about that, and he says that pixels are good modelling devices, but they can be easily misused and they can become a handicap to analysis. The reality of most systems, in fact, is that they interface with pixels more like this. And there's a whole lot going on inside pixels that can be easily overlooked by uncritically adopting a pixel-based view of the world. And then it gets slightly more complex. This slide moves on from the sort of concrete definition of the edge of a pixel and talks to a sort of more technological concern, because pixels also have something called a point spread function, which means that the signal that is measured in a pixel is actually influenced by things outside of the pixel's material boundaries. And furthermore, the pixel signal is unevenly influenced by things inside it. So objects near the pixel center will have a greater influence on the pixel value than things towards the edge. And this point spread function can vary from sensor to sensor and also from pixel to pixel. This is a really big uncertainty in remote sensing data that can be easily overlooked and lead to ambiguous artifacts in images. And this then gets really complex, but this is the complex bit that I really like, because when you consider that a remote sensing device is just measuring a voltage or a current which is sensitive, hopefully linearly, to light, you then start to get into this complex field of radiation measurement, which is effectively a three-dimensional field, both in regards downwelling as well as upwelling light. And the pixel signal is therefore a measurement of that light, which is a dynamic thing, changing not just with seasons, times of day, latitude, and those kinds of things, but also with angles of illumination and view. So the same thing with the same physical properties, measured or illuminated differently, could have a completely different apparent reflectance. And this is work that's been done by sort of fundamental physicists. On the left, Nicodemus in 1977, which is a really nice paper on the geometrical considerations of light, but more recently by Gabriele Scheitman-Strub at the University of Zurich. And that manifests in interesting but also complex ways. So this is the same tree, imaged one day apart, so we can assume that the sort of biophysical or biochemical properties of that tree crown are consistent. In the middle is an image captured under cloud shadow, and on the right an image captured in full sunlight. And what you see is the manifestation of that BRDF, the bidirectional reflectance distribution function, the variable reflectance with angles of illumination and view, changing the pixel signals under those different conditions. So we just have to be really careful when we engage with this pixel view of the world, because this tree is quite different in the image, but in reality it probably isn't.
So this is an example of a habitat site here in England. This is somewhere that I'm studying for my PhD. It's a candidate site for BNG. And if we first look at the satellite measured representation of reality, the image is already shaped by the trick of the pixel and the trick of the light that Karen is abstract a little further away from reality. So in my research, a lot of the time I receive from the ecological consultancy what is in a vector format, and these discrete simplified shapes represent habitat boundaries of land cover types. And these vectors are then rasterized, converted into pixels, each one assigned a single value. And at each stage, from the image to the vector to the raster, we move further from the physical landscape and deeper into interpretation. And this is something we need to keep in mind. Even before we fed the data into a machine learning model, we've always introduced assumptions, simplifications, biases, and then potential inaccuracies. And how often is this abstraction chain and the assumptions that come along with it even considered within a machine learning workflow?
Okay, so it was great yesterday. Someone gave a talk and they were talking about Tobler's first law of geography, and I really like Tobler's first law of geography. So the second trick that we'll talk about is the trick of scale, because when we move beyond the bounds of the pixel, what we start to see is something that speaks to the real power of Earth observation data and its broad appeal, and that is that we don't just get discrete observations, we get neighbourhood kind of data. And Geography 101 tells us that things in space that are close together are more likely to be related than things that are further apart. And that context can be quite fundamental in carrying all kinds of geographic, ecological, or environmental information. But I think this is often overlooked in machine learning workflows. If we also go to the work of people like my really good friend Jennifer Dungan, who's a NASA scientist from Ames, she's done a lot of work on scale and grain and the philosophy of that, and it brings us right back to the trick of the pixel, because the spatial context is a function of the grain. So when we choose one Earth observation product over another, we will ultimately find that things like relational or scale-dependent processes will be differently represented, and that can fundamentally change statistical relationships between things. And my concern is that in Earth observation right now, there is a hyper-focus, but from companies as well as from users, moving to finer and finer grains of observation and adopting workflows that focus on data products with smaller pixel sizes. These are more readily available now than ever before, but we shouldn't take that step to finer resolution data uncritically because, as you can see from here, I did a little calculation a couple of days ago where I looked at a sort of Landsat pixel and then I looked at how many other pixels lie inside of that. And this is a consideration because as we move to finer and finer grains, we sort of exponentially increase the data volume, such that the number of 10 centimetre resolution drone pixels inside a Landsat pixel is 90,000. So we see huge steps up in processing inefficiency when we move to finer and finer resolution. So we have to, I guess, not blindly accept data at a particular resolution, and we need to query whether the resolution that's provided is optimal for our application. And as I said, a crucial consideration is what data set should we choose and why, and we're blessed with a bigger choice than ever before. Now, thankfully, some of those old school remote sensors sort of did some cool stuff that allowed us to answer this question. So I'm coming back to Curtis Woodcock and Alan Strahler's paper in Remote Sensing and Environment from 1987, and I've recently sort of rediscovered the wonder of this work, and if you haven't come across it yourself, I encourage you to take a look. They propose a really simple approach that they call local variance. And basically how it works is, you could write this code yourself in Python in probably 10 minutes if you wanted to, or there's a QGIS grass sort of plugin that allows you to apply this to any image set. And the underlying approach is that you start with a reasonably fine-grained image, you pass a 3x3 moving window over the data set, but you could configure that window to be whatever size you want, and it moves across the scene and records variance across that entire image as an average. Then you coarsen the spatial grain progressively and repeat the process, and it produces a graph like the one on the right, where the local variance in that 3x3 window averaged over the scene is then shown in relation to the spatial resolution of the data. Now, that shape of that graph is really fundamentally related to the physical size of objects in the image, and if the spatial resolution is considerably finer than the objects in the scene, you will have lower local variance. If the objects approximate the size of the resolution cells, then the likelihood of neighbours being similar decreases and the variance will rise. And as the size of the resolution cells increases and many objects are sort of aggregated in a single cell, local variance will decrease again. So you see, this is telling us about the spatial dynamics of the image. And just to give you two quick examples, this is an example from their work, which is an image of a golf course. You see these peaks in the image, one at 15 metres and one at 40 metres, and those correspond to average distances between fairways and also the average width of the fairways in this golf course. Another example applied to Worldview 2 from some work that Andy and I have been doing. This is an area in New Mexico covered in sparsely distributed juniper trees. And what you notice is a big peak at 5 metres. That's the size of a juniper crown. And then you see these other peaks occurring at different spatial resolutions, and those are the spacing between the trees. And so you hopefully can see that this is a potentially very simple yet very powerful tool in engaging with the spatial information in the scene.
But when I look at my graphs, they're not that simple. I look across a habitat in the UK, and this is an agricultural area, and you can see that what you see mostly in green are different grasslands, but then on the other side of the road with the really bright image is an area of a university. So if you apply this local variance approach, I've done it over the blue, green, red, and red edge 2-band of Sentinel-2. You can see that we have some quite interesting patterns. For the blue, red, and green, although they show they show a similar trend, what you see in the red edge is completely different. And so it's interesting to think about why this happens. And it would be necessary to query that physical reason for why that happens, but I haven't done it yet because it's early in my research. But what's really interesting is that if you then chop off that university, those local variance graphs now completely change. And so again, you see this blue, green, red following a similar pattern, but now the first peaks in the visible wavelengths actually occur around 38 meters. So this seems to imply that if BNG is being applied within an agricultural landscape, it may be possible to downgrade the spatial resolution, which I'm currently using Sentinel-2 at 10 meters, to something that could potentially move to Landsat data with 30-meter resolution might be sufficient. But note, again, the red edge 2, although displays a different trend to the blue, green, red. So this has big implications when consider first the computational efficiency of using coarse resolution data for different habitat sites, but also that some BNG projects in urban zones might require finer grained data than what we have here. So I think it's really time to kind of visit these earlier techniques of these what's called old school remote sensing approaches to help optimize how we design machine learning workflows. And these techniques could provide valuable ways of improving the feature representation before it even reaches the machine learning or deep learning model.
Yeah, and I guess just sort of interestingly, we're happy to accept that things like sort of variant spatial resolution are okay within GIS, so probably many of us use things like triangular irregular networks for representing topographic data. For example, bigger triangles occur where topography is more level, over larger length scales where smaller triangles exist in areas where the topography is steeper. So there's already sort of models that exist in the spatial domain that allow us to consider that we don't need to have uniform spatial resolution over an entire scene. This concept of sort of scale dependence is alive and well, but it doesn't necessarily seem to be regularly used in machine learning.
And then there's that a strong importance of not forgetting the fundamental principles of remote sensing, like the spectral signatures, and understanding the spectral signatures of different classes and exploring how these are distributed in the spectral feature space remains critical. So the problem with the real world is that spectral signatures in reality may look very different from the typical signatures that are shown in textbooks, which you see on the left-hand side for you, whereas what I have on the right-hand side is what I see across that landscape I showed you before. So it's really interesting just to even be able to display this at the beginning of the workflow, because here you can see where some of the spectral, at what wavelengths or what particular bands in Sentinel-2 might be more important compared to the others. And in this case, you can see certain bands may be more useful because we have less of that overlap, but also integrating additional features such as topographic variables will probably play a critical role in class separability because of this large overlap that you can see here between rivers and lakes, heathland, and the wetland as well.
Okay, so with the enormous choice of data and variables to feed into a machine learning model, we also have to be mindful about the trick of the data volume, and that is when you add more features, you increase the number of dimensions in your feature space, and high-dimensional features tend to be very sparse. This is great in some regards. We have a better opportunity for class discrimination, but on the other hand, we have a bigger computational challenge, and we mustn't forget that this has the potential to create data monsters. So this is a plot from my PhD showing, this was quite a long time ago, showing really high levels of cross-spectral band correlation and covariance from a hyperspectral image. And you can see high levels of covariance and correlation within specific spectral regions. And this points to a necessity for feature selection.
And so here I'm showing just a small subset of features that I could potentially use in land cover classification, but in other areas of research that might actually have hundreds or potential hundreds and hundreds of different features that we could use, and the question becomes which ones actually matter. And it's tempting to throw everything into a model, especially with machine learning making that technically easy, but that often leads to overfitting, noise, and models that work in one location but fail elsewhere, reducing generalizability. So here is where feature selection becomes critical. But more importantly, every feature we include represents some underlying physical process: reflectance, absorption, the vegetation structure, the topography. And when we choose features, we're shaping what the model sees in that landscape. And this is the machine vision that Haraway describes and critiques, and that carries responsibility. If we don't return to those fundamentals, asking what the signal is really doing, what the sensor is actually measuring, and whether the feature represents something meaningful, we risk building these models that appear powerful but tell us very little about the real world. So, for example, if you look at NDVI, we know that saturates at really high level of leaf area index, but it's, this crucial insight could be overlooked. So the physical principles should be sound if you want to make a generalizable machine learning model.
Okay, so next we consider the semantic trick. When we build a land cover map, like Brie was explaining, we're turning continuous numerical data into a categorical data set. Everybody understands that process. But that's a conceptual step that moves beyond the reality of the numerical data. So we're going to go back to Menti. If I asked every one of you to use 3 words to describe a forest, we're going to do that using a poll. I'm guessing that everyone is going to use slightly different words. So if we go to Menti, if you could just all quickly type in some words that you might use to describe a forest, I think we're going to see a sort of emerging word cloud that is quite complex as a result of that. So while you're doing that, what you'll see is that the vagueness in the semantics can lead to uncertainty, and this may have impacts on the perceived utility of the final product. Critical geographers like Lex Comber at Leicester have done some work sort of grappling with this, and I'll show you a link to their paper in a moment. And we're not alone in sort of having many descriptions of things like forests. So there's a reference on my slide, which I'll show you in a moment, which explores that in more detail, showing that people can't even agree on what defines a tree, right? So there are, there's a whole, this is really interesting. Thank you for your contributions there. But you'll see that, this semantic uncertainty is something that we maybe need to explore, and this is somewhere where machine learning might actually be able to help Earth observation people out.
So one area of my research is looking at vision language models, and that is using different forms of modalities to try and help land cover classification. But when we're seeing these vision language models, semantics are they're being increasingly integrated into deep learning frameworks, and more recently included within remote sensing applications. So these models learn the semantic representations by jointly trained on pair visual and textual data, and they're being applied to a range of different varieties in remote sensing tasks, such as what I'm using in land cover classification, to scene understanding, to image captioning, and where contextual interpretation plays a crucial role. This leads to that idea of the semantic trick. Given that there's many definitions, as we saw for the term forest, which specific word or concept does the VLM actually rely on, and why? And does that matter? So in my work, I'm really focusing on that text side in the land cover classification, and central to that and understanding that is the ontology. So the chosen terminologies, the class definitions, and the hierarchical structures of how land cover is represented and interpreted within the model. But the specific wording and labels are crucial because they influence how the machine learning model learns and generalizes about geographical phenomena. And my research is looking at how detailed this needs to be and at what level the model needs. But where do we get that text? And that's, with that idea that forest can mean so many different things, what words are important for the vision language model? And as this is a relatively new area of research, it's clear how semantics influence these models, and what actually goes into the model is not yet fully understood, particularly in the context of applying remote sensing to address ecological problems. And so even if you just have a look at a Tisney plot, which illustrates the choice and detail of language that influences model learning, a Tisney can help visualize habitat classes generated before and after training a vision language model. And this projection reveals how different land cover clusters in learned feature space. And even within academia, where vision language models was used to help with land cover classification, a t-SNE plot was used, and the wording they used to describe it simply said the interclass distribution is messed up. And if we look at the feature space after, the separability is greatly increased. But I think if we're using this sort of vision language model, I think we need to interrogate this sort of information more. What exactly is causing the models to group in certain classes in this specific way? Is it the visual similarity of the images? Is it the wording that's used in the training data? And if it is the wording, what wording or phrases? And while this t-SNE plot gives us a visual handle on the structure of the data and the model's internal representation, what is it that makes it change? And I think this goes back to what was spoken about yesterday about the use and the importance of explainable AI and trying to use explainable AI to really break down what's actually going on for each habitat class and why this feature space change.
Okay, this is our final bit, so we'll get to the end in a moment. So the final trick is the trick of accuracy, and I think this is a really important one because often what we see, I think particularly in machine learning approaches, is that the goal is to maximise accuracy or some measure of accuracy. And in this move towards more sophisticated algorithms like random forests or support vector machines, those choices have been made away from perhaps some of the sort of older statistical classifiers because they are asserted to offer improved accuracies. But the problem with accuracy, particularly if you take Haraway's frighteningly inert stance, is that accuracy metrics can mislead. And as modern scholars have shown, see the examples on this slide here, trying to maximise accuracy as the be-all and end-all of your process can sometimes be a fool's errand. Because lower overall accuracies may not always mean that your product is worse. Okay, from my point of view, it would be nice to see a more critical stance being taken within the Earth observation and machine learning community around this. Are we dealing with a marginal gain in the usability, for example, and what is the computational environmental cost of shifting your accuracy from 87 to 89% or something? It's really important to look behind the accuracy measures and delve into the detail of things.
So an example of earlier on in my research when I was developing the vision language model is I got an overall accuracy of 92%. And on the surface, if you just read that, you're like, amazing, that's fantastic. But actually breaking it down, you can see I was missing priority habitats within the UK HAB classification. So for instance, heathland and scrub was being classified only at 34%, whereas it was pretty much the same amount, 32%, being classified as grassland. So this was same for true for wetlands, which was regularly mistaken for grassland as well. So it might seem obvious to carefully break down the performance by class, but that isn't always the case in research, and it may not be evident where exactly where it's happening, especially to the end user. So I think it's this breaking down and really reporting on this is crucial. And then we move on to trying to decide between different models where we're continuously comparing models and we're looking at the accuracy and we're like, great, 2%, 3%, but what stage do we stop, especially when you're looking at a 90% increase, when you're looking at 90% accuracy to begin with. And so this is where the importance go back to what I've said before, is looking at who the end user and who this model is actually for. And so it isn't just a few gains in accuracy, it becomes crucial to balance the technical accuracy with ecological relevance. And these interpretations must be grounded in ecological and practical context of the study, not just in technical metrics. So I've kind of thought about this in a flowchart, and to fully realize the potential, its application must be grounded in those fundamentals of remote sensing that we've spoken about today, with a clear understanding of who will be using this information, how decisions are being made, and what matters to those decision makers. So currently, much of the research produced within academia happens in isolation, often disconnected from these end users. And at the same time, what's done in industry is sometimes not connected to academia. So what really matters is how these models contribute to governance, policy, and ultimately to solving environmental problems. Then looking at key stakeholders, including practitioners, policymakers, and local communities, not be treated as passive recipients at the end of the pipeline. They need to be active participants in the entire process of the model development, from framing the question to interpreting the results, and crucially, helping researchers identify which part of the model development process needs focus and refinement to ensure the outcomes are meaningful for real-world applications.
Okay, so to conclude, and I'm not looking at Andy because I know he's going to be throwing visual daggers at me for the time. What we've got to be careful of is this, right? We're trying to bang a square peg into a round hole, and we can't and mustn't forget that remote sensing data are fundamentally measurements of light, integrated over a pixel, which is an imperfect model representing the real world. And if the desired class is the round hole, then we can't expect that measurement of light to be perfectly representative of some category, because nature and light doesn't work like that. So with machine learning, the hammer in this case, we have to be really careful that we're not hitting the square peg too hard, because if we force it into the hole with too great a force, we will end up with something that isn't generalizable, in some ways perhaps not even really meaningful. So this is quite a delicate process. So to conclude, these are our kind of finishing points really. The rise of machines does not absolve us of the need to consider critically the core physical, semantic, ontological remote sensing factors. And in this era of what Haraway calls the technological feast, we need to really urgently ask ourselves the question about how we best use the data and the tools at hand, whilst avoiding this unregulated gluttony that increasing amounts of data present and the promise of machine learning presents. And we need to remain alert to machine vision, which can generate a real disconnect with real-world processes, something I think Haraway is talking about when she talks about the techno monster. And I guess finally that brings us back to the point that Brie was last making, which is we should not overlook the importance of situated knowledge. In this view from above, we can lose sight of the real processes. So I think that in this age of machine learning and remote sensing, there is an increasing need, if anything, for more of this kind of work, where we get out into the place which we're studying and we understand what is actually there. And so that's the end of our talk. Thank you. Sorry for running over.
Fantastic.
It was hard to do it with
And thank you for the brilliant double act. That was beautifully interfaced. We've got time for one quick question to Paul. Paul Harris. Where's Paul? The next presenter.
Here.
Oh, if you'd come up with
A question to the collective.
Okay, go for it. Well, Karen, you choose the question.
So a lot of the points that you made there will influence uncertainty, which you didn't mention. So uncertainty, classification uncertainties and stuff. So it's important to recognise that when you're thinking about risk. And if you don't account for many of those things, your uncertainties will be more optimistic. So it's just a comment, really.
Yeah, absolutely.
Repeat the question, please.
It was a comment that all of the things we talked about will do something to change the uncertainty of the model. And if you don't account for those uncertainties appropriately, then you will probably end up underestimating your model uncertainty.
It will be more optimistic.
Your model accuracy.
Thank you.
Okay, we're happy to take
Conversation.
questions over coffee. Yeah.